Welcome to this foundational lecture on electrical measurements. Today we begin with the electrical circuit and its components. Let's dive deep into not only what the circuit components are, but why they behave the way they do from a physical, intuitive perspective. Let's begin with the definition of an electrical circuit. An electrical circuit is a closed path through which electric charge flows. But what is flow of electric charge really? Let's break it down. Every material is made up of atoms. Within each atom, we have a cloud of electrons orbiting a nucleus. In conductors like copper or aluminum, some of these electrons are free to move. When we apply an electric field, these electrons begin to drift in the direction opposite the field, forming an electric current. From a physical standpoint, the circuit is a network that organizes this electron movement so it can be useful to light up a bulb, spin a motor, or transmit data. Now here's something subtle yet profound. Electric current is a collective behavior. A single electron's motion is random and chaotic. But inside a wire with millions of electrons, their behavior becomes statistically predictable. That's the beauty of physics, order emerging from chaos. So a circuit is like a well-governed city of electrons, with resistors, capacitors, inductors, and voltage sources acting as the institutions shaping their flow. Let's now look at the basic components, not just by definition, but by their physical nature. Let's start with voltage source. A voltage source is a device that maintains a fixed potential difference between 2 points. But let's go deeper. In a battery, chemical reactions push charges from one terminal to the other, creating a separation of charge, a potential energy gradient. Think of it like a water pump lifting water to a higher elevation. Once it's up there, it wants to flow down. Similarly, the voltage source creates an electric pressure. An ideal voltage source can maintain this pressure no matter what, while a real source will have internal resistance. This is the cost of reality. Physically, the voltage is the work done per unit charge to move a test charge between 2 points. That's why its unit is the volt or joules per coulomb. So voltage is a measure of potential energy per unit charge. That's the currency being exchanged in an electrical system. A resistor is the embodiment of opposition to current. But where does this opposition come from? At the microscopic level, as electrons move through a conductor, they scatter off atoms, imperfections, and vibrations. This scattering dissipates energy as heat. This is Joule heating. So resistance is not just some mathematical constant, it's a direct measure of how disorganized interactions at the atomic level convert electrical energy into thermal energy. Mathematically, we express this with Ohm's law. V equal to I times R, but physically this means the more resistance, the more energy per unit charge must be spent to overcome microscopic chaos. Now let's talk about capacitor. A capacitor is a device that stores energy in the electric field between two conductors. Physically, when you apply a voltage across two plates, electrons accumulate on one plate and deplete from the other. This creates an electric field. And an electric field stores potential energy. Unlike resistors, capacitors don't dissipate energy, they store it. That's why they're used in filters, timing circuits, and memory systems. Its fundamental law is Q over the V is equal to C, which means the charge stored is proportional to the voltage applied. The proportionality constant C, the capacitance, depends on the area of the plates, the distance between them, and the material dielectric in between. Intuitively, a capacitor is like a spring for charge. It resists changes in voltage the same way a spring resists changes in displacement. Last component that we are going to talk about is inductor. The inductor is perhaps the most fascinating component. It stores energy in magnetic fields. When current flows through a wire, it generates a magnetic field. If that current changes, the magnetic field changes, and nature resists this change. This is Lenz's law. So an inductor remembers the current. It resists changes in current just as a flywheel resists changes in rotational speed. This behavior is captured by V is equal to L times di over dt, where L is the inductance. It's like inertia for current. A sudden change in current produces a large voltage like slamming the brakes on a moving car. So inductors are essential in smoothing out current, storing energy temporarily in magnetic fields, and enabling oscillatory circuits. To analyze a full circuit, we need the laws of conservation. In electrical circuits, we have two primary conservation principles. The Kirchhoff's current law states that The sum of currents entering a node equals the sum of currents leaving it. This is just conservation of charge. Charges can't vanish or appear, they just move. Imagine a traffic roundabout. Cars entering must equal cars exiting, or you get congestion or emptiness. The same is true for electrons. On the other hand, the Kirchhoff's voltage law says the sum of voltage drops in a closed loop equals zero. This comes from conservation of energy. If you walk around any closed path in the circuit and return to the same point, the total energy gain and loss must cancel. Voltage drops across resistors, rises across sources. When you sum them all, you return to the same potential. A final key concept is the lumped element model. In this model, we assume all the properties, resistance, capacitance, inductance, are concentrated into discrete components. This works well when the physical dimensions of the circuit are much smaller than the wavelength of signals involved. It's why we can treat a resistor as a single object even though it's really millions of atoms. But at higher frequencies or over large scales, this model breaks down, and we need distributed models and Maxwell's equations. To summarize, a circuit is a physical manifestation of controlled energy transfer through electron flow. Voltage sources, resistors, capacitors, and inductors are not just theoretical elements. They each reflect distinct physical phenomena. Kirchhoff's laws enforce conservation principles that guide all analysis. The lumped element model simplifies our analysis by treating complex distributions as discrete elements, but it has limits. Understanding circuits at both symbolic and physical levels empowers you to not only build systems, but to deeply understand them. In the next discussion, we will move from concepts to measurements. How do we actually observe and quantify these behaviors? Thank you, and let's continue mastering the physics of electricity, one concept at a time.